Welcome to this explainer. You know, have you ever wondered how a tiny, lightweight four-cylinder engine can just easily outmuscle a much larger, heavier V8? Well, the secret lies in a machine with rotors spinning at up to 250,000 RPMs. Think about that for a second. That is actually faster than many jet engines. Today we're going to dive into what I like to call the hero's journey of exhaust gas, and we'll see exactly how a turbocharger transforms literally wasted energy into absolutely incredible engine power.
We've got a lot of fascinating ground to cover today. We're going to start with the fundamental problem of wasted energy, break down the anatomy and that step-by-step boosting process, and then explore how engineers actually manage to tame these extreme pressures. Okay, let's just dive right into this.
All right, Section 1, the power of wasted energy and how we recycle heat and pressure. So, every automotive engineer faces this one basic, unavoidable problem. Engine power is fundamentally limited by the amount of air and fuel that can physically get into the cylinders. Normally, a massive amount of energy is simply blown out the tailpipe as hot exhaust. It's just wasted. But the turbocharger steps in as the ultimate recycling system. It uses that rapidly exiting exhaust to force highly dense, fresh air right back into the intake. It's brilliant. Moving on to Section 2, let's look inside the machine and break down the turbocharger anatomy. When you look inside, there's a very clear division of labor. On one side, you have the hot turbine section, which collects those glowing, hot, high-pressure exhaust gases. And on the other side, you have the cool compressor section, which draws in and pumps the fresh air. But here's the absolute most crucial detail. They share a single central rotating shaft. So when the violent exhaust spins the turbine, the compressor on the other end literally has no choice but to spin right along with it. They're locked together. Now, that shared shaft is suspended by bearings hidden inside the center housing. And because we are dealing with those astronomical speeds of up to 250,000 RPMs, friction is your absolute worst enemy. While traditional oil-lubricated journal bearings have been the standard for years, modern ball bearing cartridges are just a massive upgrade. They can spool up to 15% faster and use half the power, which gives the driver an exceptionally crisp throttle response. It's a real game changer. Okay, Section 3, the step-by-step boosting process. Let's map out this airflow cycle. To understand how these parts move air in a continuous loop, you just have to follow the path. Fresh air gets sucked in, it's compressed, it's cooled down, then it enters the engine cylinder to burn with the fuel, exits as hot orange exhaust, spins the turbine, and finally leaves the vehicle. It's just this incredibly elegant, continuous loop. Let's actually walk through that step by step. Step 1, the compressor aggressively squeezes the incoming air, which naturally heats it up. Step 2, an intercooler cools that compressed air back down to increase its oxygen density. Step 3, this newly dense air enters the intake manifold. Step 4, the cylinder burns this rich, packed mixture of air and fuel. Step 5, the violent expansion of that exhaust gas forces the turbine to spin. And finally, Step 6, that turbine mechanically powers the compressor, starting the whole loop over again. This pressurized air creates what is known in the engineering world as boost pressure. And this is the magic word. Because the air is packed together under high pressure, a massive amount of oxygen is crammed into the cylinder. And more oxygen means the engine can burn more fuel in the exact same footprint. Really, this is the secret to how a small, lightweight engine can produce the raw horsepower of a much larger one. Which brings us to Section 4, controlling pressure and surge. We've got to tame the beast. So here's the catch. If you let this cycle loop unchecked, boost pressure will rapidly, and I mean rapidly, climb until the engine literally blows itself apart. Boom. To tame this, engineers rely on two absolutely critical relief valves, the wastegate and the blow-off valve. Both of these use pressure signals and heavy spring forces to keep the turbocharger operating safely. Here's how they divide the work. The wastegate sits on the hot side. It acts as a bypass, bleeding off excess exhaust gas around the turbine wheel so it simply doesn't spin too fast. The blow-off valve, on the other hand, sits on the cold side. Imagine rapidly taking your foot off the gas pedal. The throttle plate snaps shut, but the turbo is still spinning at hundreds of thousands of RPMs, pumping air. The blow-off valve quickly vents that compressed intake air to prevent it from bouncing backward and causing a destructive shockwave, which is known as compressor surge. Section 5, let's talk about the pros, the cons, and of course, turbo lag. Harnessing these extreme pressures comes with some very distinct trade-offs. On the plus side, the benefits are undeniable. We get incredible torque and horsepower from significantly smaller, lighter engine packages. This downsizing naturally leads to lower fuel consumption and reduced exhaust emissions. Plus, and this is a really cool feature, a turbocharged engine prevents power loss at high altitudes. While a normal engine is literally gasping for breath in thin mountain air, a turbocharger simply compresses that thin air to maintain sea-level power. It doesn't even break a sweat.
However, there's always a however. The downside is a massive increase in plumbing, maintenance, and extreme heat generation. When you shut off a hot turbocharged car, the residual heat can literally bake the stagnant oil inside the center housing. It turns it into a hard sludge. This is a highly destructive process known as coking. Because of this, modern systems require strict engineering for water and oil cooling to act as a heat sink.
But without a doubt, the most famous drawback is turbo lag. This is that slight, sometimes frustrating delay you feel between pressing the throttle and the engine actually surging forward with power. Because the system relies completely on exhaust, the turbine literally has to wait for engine exhaust gases to build up before it can start spinning fast enough to compress the intake air. It's a waiting game.
Section 6. Real-world applications and how we're actually combating that turbo lag.
To combat drawbacks like lag, engineers have developed some genuinely fascinating variations. Take the regulated two-stage or twin-turbo setup, for example. This brilliantly pairs a small turbo, which is designed for extremely quick low-speed response, with a much larger turbo designed for massive high-speed power. By handing off the airflow seamlessly between the two, it effectively erases turbo lag entirely. It's the best of both worlds. Another brilliant solution is variable turbine geometry, or VTG. Now, instead of a fixed housing, VTG uses tiny, moving guide vanes inside the exhaust housing. The engine's computer continuously adjusts the angle of these vanes to physically change the exhaust flow dynamics on the fly. Essentially, it squeezes the exhaust gas at low speeds, keeping the turbine spooled up constantly. It's like putting your thumb over the end of a garden hose to increase the pressure. Yet, regardless of how advanced the technology gets, there is one universal rule for keeping any turbocharger alive. As a driver, what do you think is the single most critical habit for maintaining a turbocharged engine? The answer all comes down to lubrication. Because these delicate bearings spin at those astronomical speeds with extremely tight tolerances, you absolutely must let the engine idle when it's first started. This gives the oil pump time to push clean, pressurized oil up into the center shaft before you step on the gas and ask it to spin up to full speed. A little patience of about 60 seconds saves a whole lot of expensive hardware. Ultimately, the turbocharger is just a masterpiece of energy recycling. It takes the heat and pressure that we used to literally throw away out the tailpipe and forces it to do hard work. It's the sole reason modern engines can be smaller, lighter, and vastly more efficient without sacrificing the power we love. So as we look to the future of automotive engineering and the global demand for even cleaner, greener engines continues to grow, it really leaves you wondering just how much more untapped potential can be squeezed out of this incredibly vital machine. Thank you so much for joining this explainer. I really hope this helped you understand the fascinating hero's journey of exhaust gas.